Welcome back. So we were talking about turbulent flame speeds, and we will go into some experimental configurations. So just to recap on the concept of turbulent flame speed, and what we just did was that we took we essentially took if you take a cuboid channel like this, okay. Before we go into the experiments, we just want to show you something like this. That is, suppose this is a cuboid in which you want to basically find out the turbulent flame speed. I just did this a little bit in a simplified manner, but before we go into the experiments, let's discuss this in more details. And here you have the turbulent flame which is stabilized, just like the movie you saw. Okay, so this is your turbulent flame. Okay, so now. To give you a more details, so now each of these points essentially say if we say consider an infinitesimally small area on the flame and represent this by dA, and the relative velocity of this flame surface with respect to the local fluid velocity is of course SD in the normal direction, right. So this is essentially SD dot n vector times dA vector, so it gives you SD times dA. Okay, so now the total mass flow rate that is entering into this whole surface, we can write this as m dot is equal to integral over the entire surface rho times, if it is close to the unbound side, then it's of course rho times we can approximate this as essentially rho u times SD times dA. Okay, so so this is the rho u times the local displacement flame speed times the dA, and now that is equal to, we can if we now want to represent this whole mass flow rate into the fuel air mixture by one average velocity of the fuel air mixture, then that is the turbulent flame speed. So then that is given by rho u times ST, and what is the area? Area is of course this is the area which is this project area which is given by A. Okay, so this is A, and let this area is be equal to full this thing is equal to AT. So then this is rho u times ST times A. Okay, so this is now you see where does ST come from. So now we can simplify this if we assume that SD is equal to SL over the entire flame surface, we do not consider any effects of stretch. So then what you get is that to the leading order, rho u is, if this is an isothermal surface, then rho u cancels out. So rho u cancels out. So then we get ST times A is essentially SL, this is over the entire surface area, so this is AT. So then ST is essentially equal to ST by SL is equal to AT by A. So of course this comes into the assumption that you have assumed that SD is equal to SL over the entire surface, which is not true, but still what you see here is that even then to the leading order your ST by SL is essentially equal to is close to AT by A, and in fact in reality also your ST by SL is close to AT by A, and your ST that is a turbulent flame speed is much more than the laminar flame speed, is simply due to the fact or the overall propagation rate of the flame surface is much greater than the local propagation rate of the flame surface. This is simply because you have turbulence has generated a very large flame surface area due to stretching and wrinkling over a multitude of length and time scales. So because this area of the flame is much more, it can consume the fuel air mixture at a much faster rate. Okay, and it can, that is why it can essentially propagate on average, it can propagate much faster than the planar laminar flame. So this is a remarkable property of the turbulent flame which is utilized in different engines. So that is why I was saying about gas turbine engines, you can have a flame stabilization at high speeds in a gas turbine engine because your turbulent flame speed is much higher than a laminar flame speed. In a car engine it can produce a lot of power by consuming a lot of fuel without producing pollutants, is because your turbulent flame speed allows, if you have a lot of turbulence inside the engine, it allows the propagation, the flame to propagate much faster than it can, than a laminar flame can propagate. Okay, so the turbulent flame speed is a very, very important thing, and from here you can clearly see that why your ST by SL is much greater than 1, because your AT, that is this wrinkle flame surface area, is much greater than the projected area or the area of a planar laminar flame. So next we will show you how we will determine the turbulent flame experiments. So it's not a simple experimental setup. So this is comes from Kobayashi's group in Tohoku University, and reported in this proceedings paper in 1996. So here they have a high pressure turbulent Bunsen flame setup. So this is where your flame is actually. So you see the flame to be essentially. So the flame is essentially here. Okay. So this is the flame, if you can see, and then there are like many diagnostics. Of course, this experiment has to be placed in a very high, very thickened walled pressure vessel, and then you need to have optical access so that it can the flame motion or the flame surface can be visualized with a CCD camera using Schlidian techniques, which will give you the density gradients. Okay, and so then it also measures the local flow velocity fluctuations, because as we remember, we want to get the turbulent flame speed as a function of the URMS. That is of course one of the important parameters. You can get planar laminar flame speed and the flame thickness from either by experiments or by, you cannot get flame thickness by direct experiments unless it's a very high end experiments using different probes like synchrotron, etc. In a synchrotron, etc. But you can get them easily by using this Chemkin tools, Chemkin premix tools. So the planar laminar flame speed and the flame thickness can be obtained easily. So we wanted to obtain ST as a function of U prime 0, L0, which are the flow parameters. So these are the flow parameters, and SL, the planar laminar flame speed, and LL. So this needs to be measured, and whereas this can be computed, so this needs to be measured, and for a given phi and a given fuel air mixture, and for a given pressure, your SL and LL can be calculated using Chemkin premix or Cantera. Okay. So these things can be calculated. So once you have, if you can measure the turbulent flame speed, if you can measure U prime 0, and if you can measure the L0 and calculate SL and LL, then you can essentially find correlations between turbulent flame speeds and these parameters. So how do you measure turbulent flame speeds? Now before we measure, let's show you some different structures of turbulent flames. So this is, you see that at the same flow velocity, okay, if the flow velocities remain same at U average is equal to 2 meters per second and same hole diameter of 2 millimeter. So this on the left hand side, you have the turbulent flame behavior at low pressure and then at high pressure. Of course, this is one of the artifacts. If you do the same flow visualization also, you will see that high pressure your flow has very small scale structures with respect to the flow at low pressure. The reason is that once again, if you remember, your eta by L0 is essentially Reynolds number to the power of minus 3 by 4. Okay, so and Reynolds number you see is essentially rho V D by rho URMS U prime 0 times say D by or L0 by mu. So if mu does not change much such with the pressure, so U prime 0 and L0, if that also does not change too much with pressure, but rho is directly proportional to pressure, right, at a given if the temperature is fixed. So it directly increases with pressure. So that is why the scale separation, the eta for a given L0, your Kolmogorov length scales become smaller and smaller with pressure. So even if you keep all the other properties constant, but if you decrease or if you increase the pressure, your Kolmogorov length scales become smaller, and as a result of that, any turbulent jet or a flame has smaller and smaller structures, because your flow has much small structures now. It's much more turbulent. That is the same reason why in an engine you have very small Kolmogorov length scales at very high pressures. Okay. So this is how a flame, another turbulent flame will look like at a pressure of about 10 bar or 1.0 MPa megapascal, whereas at 1 bar or that 1 atmospheric pressure, this is what a turbulent flame look like. So at a different pressure, your turbulent flame structure is very different, as you can see from here. Okay, and of course this being much more wrinkled, it must have a much more flame surface area. Okay, so how do you extract how do you find out the turbulent flame speed? So for that, first you have to extract the mean flame cone. So you find out all these flame contours like this, okay, and this is for one realizations. There can be for another realizations like this. So they will get a different kind of realizations, and then you can essentially average them out and find out the average. For example, the average flame cone for this will look something like this, okay, and we do some image processing to extract the flame edges and find out the mean flame edge, and it looks something like this. And then basically you say that your ST is essentially equal to u sin theta by 2, because if this flame cone is like this, then my say if my ST is like this, so then this is how I evaluate it. So say this is this one is better. So say this is my u. This is not my ST. Sorry. So this is my u. So so now I can resolve this u into the normal and the tangential component. Okay. So say this is my u, and then this is my theta by 2. This is my normal, and this is my ST. Okay. That is the mean flame speed. That is the component of u which is perpendicular to the mean flame cone. Okay, now this is the mean flame, means it's essentially statistically stationary because it has been time average. So because for it to remain statistically stationary, the flow velocity that is perpendicular to it must be equal to the global turbulent flame speed. So that is the argument by which you get this ST. Once again, that the idea is that if you have flame surfaces like this, okay, and these are the different flame surfaces that you generate, extract from the different videos, and then you generate basically a mean flame surface by averaging over all these flame surfaces like this. Okay, and then this is your say mean fluid velocity, which you know from your mass flow readings, and then you basically resolve it into this direction, into the normal and the tangential components. Okay, so this is your mean flow velocity. So this is your mean flow velocity. You resolve it into normal and tangential components. This is your theta by 2. Okay, and so then this guy. So then this mean flame surface, for this mean flame surface to remain statistically stationary, it must be fed with a flow velocity which is normal to the mean flame surface, and this flow velocity normal to the mean flame surface must be equal to the turbulent flame speed for this given configuration. All right. So then if you can find out what is the mean flame velocity normal to this mean flame surface, then that is my ST. So then that is nothing but u, this velocity is nothing but u times sin theta by 2. So then this means that my ST is essentially u sin theta by 2. Okay. So if I know my if I can extract this mean flame cone and find out the different thetas for different configurations, then I can find out what is the mean what is my turbulent flame speed. And so they did experiments for different configurations at so we see that different configurations that did experiments, and when they put this in a plot, we see that this is ST by SL and this is U prime by SL. So this is you see that this has a kind of a bending behavior, all of these curves. So like this they bend after increasing, and what we see is that as pressure increases, ST by SL increases. So this is at a pressure of 0.1 MPa, and this is at a pressure of 0.5 MPa. Okay, this is at a pressure of 1.0 MPa, and this is at a pressure of 2.0 MPa. and this is at a pressure of 3.0 MPa. 3.0 MPa is a very large pressure. This is essentially 30 bar, and you see that at this high pressure, at an U prime by SL of about 10, your UST by SL is has reached the value of about 30. So that is a huge increase over the normal planar laminar flame speed that this turbulence flame has reached. So actually the turbulent flame speed in this case, it can be shown that has not reached increased so much, but if you remember, the planar laminar flame speed decreases with pressure. So whereas the turbulent flame speed can change slightly with actual turbulent flame speed does not change too much with pressure, but it is essentially the decrease of the flame speed with the planar laminar flame speed that causes this rapid increase with pressure. So but anyways, that is an important thing, because if ST was so small at high pressure, then it would be very difficult to essentially stabilize flames in high pressure gas turbine engines. So that is a good thing. Next we will talk about in some details about this dual chamber high pressure turbulent combustion vessel at Princeton. So where many of this expanding turbulent flame experiments were done. These were also done at previously at Leeds University, and but this setup is a little bit different from those. The main setup, the main purpose is to essentially measure the turbulent flame speed of expanding turbulent flames at high pressure and at constant pressure. So to maintain constant pressure, there is a nice this setup is used. So you see, if you have a enclosed vessel, and if you increase and if you ignite the flame at the center of that vessel, what happens is that this flame will expand, but immediately the pressure will rise. Okay, but as you know that the planar laminar flame speed is a strong function of pressure. So if you do an experiment where your pressure is continuously increasing, then you are essentially changing one of your most important parameters. So you cannot do a good experiment where the most important parameter changes like that, where a independent variable like planar laminar flame speed, which is an independent variable in your scaling laws for turbulent flame speed. So you want to obtain the turbulent flame speed as a function of planar laminar flame speed, flame thickness, integral length scale, URMS, etc. So in this scaling laws, your SL and L and your flame speed and flame thickness appears as independent variables. So you cannot do an experiment where an independent variable essentially is changing. Of course, the flame thickness will also change with pressure. As you know, the flame thickness decreases with pressure, and that is one of the reasons also why you see that emergence of different finer and finer scales in the turbulent flame that you saw just for the Bunsen turbulent flame that you saw. Okay. Now the thing is that so in this setup what the people do is that we have a dual chamber vessel. So you have an inner chamber and an outer chamber, and we fill up the inner chamber with the fuel air mixture, and then we ignite that thing with a spark. So as soon as the spark is ignited, this inner chamber and outer chamber has some ports which opens up, and these can essentially communicate. So the pressure that is increasing inside the inner chamber due to this gas expansion, due to the flame, due to the overall temperature rise inside the inner chamber. So that can be absorbed into the outer chamber. Okay, as a result, the flame essentially propagates in isobaric environment. So this provides very valuable data for turbulent flame speed, and this is how essentially a turbulent flame which is ignited in this dual chamber turbulent combustion vessel looks like. So you see that this is just this is right after the spark where this kernel is formed, and you see this shock being formed right after the spark, which immediately goes away. So this is how so you see that this is how this turbulent flame is expanding. This is a false colored Schlidian imaging of the actual experiment. So you see that this flame is this is how the turbulent flame structure look like. I will again play this video. So you see that it immediately forms this turbulence from several wrinkles at different scales on the flame surface, and essentially the flame propagates very fast at the later stages. Okay, and this is a very short time experiment. As you see, it's of the order of 8.7 milliseconds, and the average radius is about 3.5 centimeters. Okay. So, these are very important experiments, and this gives you a very clear idea of how the turbulent flame structure looks like, where it is essentially stretched and wrinkled at a multitude of length and time scales. Okay, so this is how the different Schlierian imaging looks like, the black and white Schlierian images. So, you see that this is at 1 atmosphere, this is at essentially at 1 atmosphere, but so this is on this, in this matrix what we have is that we essentially denote 3 this in this way time increases for the same experiment, and in this direction the experimental conditions increases. So, in from here this is about P1 low URMS, low URMS or U prime 0. Here we represent URMS by URMS, and this is P1 moderate or high URMS, and this is P equal to 5 and high URMS. Okay. So, this is so you see that in this one as you see that this 1 atmospheric pressure low URMS, mild wrinkles are being formed, and the flame is propagating, of course, at a given average propagation rate, and then here you see as you increase the URMS, this scales become finer and finer. Okay, there is small scale structures being formed, and that is clear because once again your now the Kolmogorov length scale is actually smaller. Okay. So, in this case your essentially your turbulence Reynolds number is smaller, is larger in this case with respect to this case. Okay. But so that causes this increase of this finer scale structures, and you see that here it has reached 22 millimeter average at 6.93 milliseconds. Here it has reached the same radius at about 5.29 milliseconds. So, as you increase the URMS, it basically the average propagation speed increases. Alright. So, on this case you see that as you increase as you have gone to 5 atmosphere and URMS of even high same URMS as this, but while you have changed the pressure, there is this structure, the structure of this flame is much smaller than what you have here. Okay. So, this flame structure is even smaller than what you have here. Okay, and this is because your both your flame thickness as well as your Kolmogorov length scale has decreased in these cases. Okay. So, that causes this emergence of these finer scale structures, and it has even you see that it is even propagating at a faster rate at about 4.47 milliseconds. It has reached the diameter of 22.74 millimeter. Okay. So, then we can the observations of that, apart from this emergence of different scales in these experiments. So, in these experiments which are conducted at a URMS at of 1 to 6 milliseconds and 1 to 6 meters per second and a pressure of 1 to 5 atmosphere, and we used a high speed Schlierian imaging to characterize the flame propagation, and high speed PIV was used for characterizing the non-reacting turbulence parameters. That is an important thing, because how do you know what is your URMS? So, you need to do a high speed PIV, or you need to measure the velocity inside by LDV, etc. But the interesting thing is that if you find out the average radius, how do you define the average radius? So this is your you find out the total perimeter of the on the total area that is enclosed by the flame surface, and you say that is equal to A. So, you define the average radius is essentially is equal to A by pi. So, of course, this is a little bit it's essentially this average radius is a characteristic length scale of the flame. Okay. So, then this is how you define the average radius. So, if you now plot the average radius by extracting the image from the different from the different flames, and if you plot the average radius versus time, what you see is that first before going into the turbulent flames, if we compare it with the laminar flame. So, this is you see what is the average radius versus time for a laminar flame. Okay. So, this is for a laminar flame. You see that this is almost linear with time. Okay. So, the average radius is almost linear with time. So, but for the turbulent flames, you see that the average radius is not linear, because if it was linear it would have been something like this. So, it essentially concave upwards. Okay. So, you see the average radius versus time being linear means dr dt, okay, which is essentially a measure of the flame speed, is essentially constant. Okay. Whereas if this is linear, okay, so then it means dr dt essentially increases with time. Okay. So dr dt essentially increases with time. Now that is a very interesting thing, because then it means that essentially the flame is accelerating with time, or in the other way, as the radius is large, the flame speed is large. Okay. So there is a that is a very interesting thing that is not seen in a laminar flame. Of course, you can see a little bit of this effect when you have different Lewis numbers, depending on the Lewis number greater than or less than unity. You can have conditions where you have essentially the flame can accelerate, but it definitely cannot accelerate as much as like a turbulent flame, where you see this strong non-linearity of this average radius versus time. So this is a very interesting point, and this needs to be further probed, and then what you need to find out utilizing this. The question was that can we find out a scaling relationship for the turbulent flame. So if we plot, what we see is that if we plot y axis as 1 by SLB, that is normalized with the mean flame speed, is essentially can be taken as ST by SLB, that is a Born flame speed, whereas drdt is equal to your ST. And so if this you plot on the y axis, and on the x axis you plot this URMS by SL times average radius by delta L. Okay, so this we plot this thing, average radius by delta L. I will come into this why we come to this choice. Then you see all this experimental data can essentially collapse on this Reynolds number to the power of 0.54 plot. Okay. So we can write in this correlation, in the scaling law, we see that this law emerges, this powerful law emerges, whereas we have a Reynolds number which is based on a turbulent Reynolds number which is based on average radius, and this scales as to the power of 0.54, which is nearly to the power of 0.5. Now why do we scale with this parameter at all? That needs to be understood. First of all, the most of the experiments are in essentially the thin reaction zone regime, and you saw that by Damkoller's and as well as by our calculations, analytical work, your ST by SL for a planar laminar flame, for a statistically planar flame, can scale as URMS by SL times L0 by LL, okay, or your integral length scale by flame thickness, which is the symbol that we use here. Okay, but that was for a statistically planar flame. Okay. Now for a expanding flame, you see the flame is expanding in a cylindrical volume which contains turbulence. Okay. But okay, why is the flame accelerating, or why is the turbulent flame speed higher than the laminar flame in first place? The reason is that because turbulence has stretched and wrinkled and folded this flame surface at a multitude of length and time scales, okay, and that has caused this area, surface area, to increase. Okay. So for a statistical planar flame, all the scales of turbulence that are present, right from the integral length scales to the Kolmogorov length scales, can participate in this stretching, wrinkling and folding of the flame surface. Okay. But for an expanding flame, okay, which at a particular instant is of radius r, this statistically spherical flame, which is at an average radius r, can only be stretched, folded and wrinkled by turbulence of length scales which are equal and smaller than r, because the turbulent eddies which are greater than r, this will only convect this kernel. Okay, this will only push this kernel instead of stretching and folding it. So only those eddies which are equal and smaller than r can participate in this stretching and folding processes for this statistically spherical flame, for this expanding flame. So at a given radius r, if you look at this flame, okay, at a given radius r, only eddies which are smaller than this radius r can stretch and fold it. Okay, that is the idea. Whereas if you have an eddy which is this, okay, it cannot stretch and fold it, it can only push it. Whereas pushing it and convecting it on average does not create any stretching, does not create any new area, and hence that should not participate in the turbulent flame speed as such. So, that is why instead of L0, the correct, instead of L0, which is of course we can have a L0 in this configuration also, the appropriate choice of length scale in this problem is radius. Okay, and this was reported in our paper by Chaudhary, Wu, Zhu and Law in the Physical Review Letters. Okay, and this choice of average radius is a very important consideration, and other groups have also shown that when you use average radius for expanding flames, you can essentially collapse all the data and arrive at this kind of scaling laws. So, that is important thing, but still there is more needs to be understood about what are the different intricate mechanisms about this, that are in play in this one. So, then we show that if we take Kobayashi's data for a Bunsen flame and our spherically expanding flame by appropriate choice of appropriate length scales, we can essentially collapse the different data into one into this kind of a uniform plot. So, then we did with different experiments, and we saw that when if you just use the flame thickness, when you use different fuels whose Lewis number and Mach-Steen numbers are different, then the only use choice of the flame thickness cannot describe your turbulent flame speeds. So, then we show that then one has to use this parameter called Mach-Steen length defined on a Burnside for collapsing most of the data on a narrow band, and we showed that by using different kinds of fuels ranging from methane to ethane to ethylene to N-butane to DME, dimethyl ether, and also by using data from isooctane data from leads. Okay, so over this large variation of properties, over this large URMS as well as different pressure and different fuels, we showed that that if you use this kind of a scaling law, and that also came from this analysis, that if you use this kind of a scaling law, then you can collapse this turbulent flame speed. If you use this kind of a parameter, you can collapse the turbulent flame speed over a narrow band. So, and then the question was that this does this scaling law does it really hold depend on these two individual parameters independently? So, is it just we get this this half just by chance? So, if you just fit this data on the surface using a surface plot, and if you choose this m and n as independent parameters, and you fit whatever data you get from different experiments into over of all the experiments in this plot, then you get a m to be equal to 0.43 and n to be 0.45, which is close to 0.5. So, this way you show that this is indeed reasonably good scaling law, which holds over a wide range of conditions. And then I will show you how we can find out how the different how we can do this Mies scattering images for different experiments and PIV. So, for doing PIV, first you have to do high speed Mies scattering, and then you see that this is how the flame is expanding, and then you can find out the vectors. And of course, the fuel is the flame consumes this olive oil droplets, which was used for seeding the flow, and you can see that how the flame expands in the surrounding turbulence. Okay, and this is then we can find out the flame edge and the different things like the tangential flame speed, the tangential straining rate, as well as the curvature at different points on the flame surface, as well as the local flow velocities, which cause this wrinkling. So, then those things can be evaluated, and we found out that the URMS does not change too much with and without the presence of the flame, and that was important because all the scalings that I presented were obtained with URMS, which was obtained in the cold flow. So, question can arise that how much does the URMS actually change in presence of the flame? It turns out in this case it did not change too much with the flame, but with the presence of the flame. But one needs to do other experiments in different other configurations to find out what is the effect of the flame on the URMS, because just as the turbulence enhances the flame surface area and distorts the flame surface, the flame can can also distort the neighboring flow field due to the gas expansion. So, when the turbulent flame is or the laminar flame is expanding, it is actually pushing the surrounding gases, and that can change the local flow fields. We found out that the local average flow field changes, but the local but the URMS field does not change too much, and this was documented in proceedings of Combustion Institute 2015 paper. So, we'll that is all up to here, and in the final thing we will take up this Bray-Moss-Libby model, and with that we will close turbulent flame speed. So, thank you.